Start recording. Okay, so today we have a couple of different things that we are going to speak about, and all of them kind of revolve around money, right? And this idea of interest, right? So, just as an overview of what exactly we're going to talk about. First, we're going to talk about how money can make money. I'm sure all of you have at least heard the word interest. If you have student loans, whatever, you collect an interest on that. Or if you take any loans out, you've got a credit card, you are collecting interest on it. So we're going to start off just kind of defining two different types of interest. We're going to define what simple interest is, right? And then we're going to define what compound interest is. And the three different types of compound interest, and we're going to discuss all three and kind of tell how you can calculate all three of those different types of compound interest. After we talk about that, we're going to talk a tiny bit about investments, right? And then we're going to talk about savings plans, which is kind of tied into investments. But we're going to talk about how we can do some math on savings plans to do some calculations. And then lastly, we are going to speak about loan repayment and a way to do some calculations to figure out some loan repayment information. Okay, so let's go ahead and jump right into it. Getting started with compound interest. So this is week 4, and our first topic is the power of compounding. So again, the first thing we need to do is understand interest. Now, I'm sure all of you have heard about interest. Like we said, credit cards give you interest. Really, anytime you borrow money, you got to pay interest on the money that you borrow. So basically, interest is the fee that you pay to use someone else's money, right? So if I loan, say, Camille $1,000, when Camille comes back to pay me back the $1,000, I'm not going to accept just $1,000. I'm going to need $1,000 plus a little extra because I loaned her the money, right? So that's basically what the interest is. So money is never free. I mean, even when you sit and hold money, right, your money depreciates, and it's almost like you're losing value or paying something to basically be able to hold that cash or hold that money. And whenever money passes hands, like whenever somebody gives someone else money, the person who is giving the money collects a fee called interest. And if you hold money, like we said, your money loses value. That's depreciation. And lastly, interest. Whenever you're talking money or financial tools or anything like that, interest is one of the most important things whenever you're talking finances, right? Because almost the entire system of capitalism is kind of built on interest and the fees people pay for money. So interest rates. So it's very important that we understand how to work with interest, how interest works, and just understand it in total. So moving on, right? The first question we want to ask ourselves is, do we want to work for our money, or should we make our money work for us? So I have a little picture. Which person would you want to be? Do you want to be this person in the purple suit, or do you want to be the person with the yellow hat? Who do you want to be?
Purple suit.
Purple suit, exactly. You want your money to be working for you. But instead, what do most of us do? And I mean, I'm included in that, right? What do most of us do? Most of us, we go to work and we use our physical labor to make more money, right? That's what we do. We use our physical labor to make more money. So most people, most of us, are actually this person in the yellow hat. Hopefully, what we'll be able to do is understand some ways that as we collect more money, understand some ways that we can actually become this person right here with the purple suit. That's the hope, that we can actually become that person and understand and learn some ways and tools where we can make our money work for us. So whenever we're dealing with interest or problems that involve interest, Usually, we're trying to find out one of two things. Either we want to find out the future value, right? So what will we owe if we borrow such and such amount of money? What will we owe at the end, or what will we pay in total? Or if we invest some amount of money and we get some interest or return on our money, right? How much will we have at the end? Or we may want to know what we need to start with to end up with a certain amount. So let's say you're like, I need to save $50,000, and you have some way of investing your money. You want to be able to find out how much money would you need to start with, or how much money would you need to save on whatever period to collect up to $50,000, right? And it's not just a simple division problem, because we have interest tied in there. So you're going to get your money, and then you're going to get a little more, which is the interest. Or you're going to pay money, and then you're going to have to pay a little more, which is the interest. So whenever we're talking loans and interest, the amount that we start with, or the amount that we start by borrowing, right, or the amount that we loan initially, is the principal. So in the example I gave just a couple of minutes ago, where I loaned Camille $1,000, right, the $1,000 that I loaned Camille, that is the principal, right? So the principal is what you start with. The present value is the amount of money at a certain point in time, right? If you're talking about right now and you haven't started anything, then the present value is just whatever you're starting with, right? But it doesn't necessarily have to be what you start with. It could also be, let's say you're going to save money for 10 years. You may want to know what the present value will be after 5 years. So you haven't completed it, but you want to know how much money will you have after 5 years. And the future value, right, is exactly what it sounds like. It's the amount of money that you're going to have at some point in the future. And whenever you're dealing with money or loans or borrowing money, there is always, every single time, some type of interest rate. And that interest rate is the rate at which the interest is being added on to whatever it is. So you may know the interest rates for your credit cards. Credit cards usually have an interest rate of like 29%, something around there, right? That's what your interest rate is. And whenever you're dealing with money and interest, time is always going to be the most important factor. So if you're dealing with a savings plan, let's say you're trying to save for retirement, you got your 401k or whatever, your 203, what's 203b, whatever you have, your savings plan, time is going to be the biggest factor. The longer you have to put money into that account, the larger it will grow. And it doesn't grow in like a linear fashion. So when you're dealing with interest, in most cases, right, you may think intuitively that if you save for 10 years instead of saving for 5 years, you'll have double the amount of money. But it's not actually true. In reality, you'll have much more than double the amount of money if you double the amount of time that you save for, right? And whenever we're dealing with finances or money stuff, usually we are looking at a year as a standard period of time. And when we're dealing with savings plans or loans, we'll usually be looking at a month as a standard unit of time. So how often are you paying on your credit card? Every month. How often are you
Are you
putting
gonna
money
share
into your
these slides?
Yeah, the slides are already up online.
Okay.
Yeah, the slides are on Moodle. So you can go on Moodle and download the slides. I mean, you don't have to download it now because they're in front of you, but later on you can download them and kind of look over them while you watch the video or something like that. So when we're talking about interest, there are two main types of interest. There is simple interest and there is compound interest. Now, an important note, that word simple, it's a mathematical term, right? It's not like the word when we just think of a word being simple as in like not complicated. It's actually a mathematical term. So just remember that. You have to add that word simple in there even though it seems like a regular word. Now, simple interest is when you calculate interest only on the initial amount that you borrow or the initial amount that you loan out, right? That's what simple interest is. And with simple interest, you pay the same amount of interest every year. That's why it's called simple interest, right? Because you're paying the same amount. The amount you pay does not change. And again, the key thing here is that simple interest is only paid on the initial principal. Only. It's not paid on any other amount. It's just paid on the initial principal. So let's look at an example. So in this example, we're borrowing money from a bank, and Afia is borrowing $2,000 at 5% annual simple interest, right? And the question is, how much will she owe after 5 years? Right. So I know we could go back and write down the definitions, but it's much easier to understand it if we go from the perspective of looking at it with an actual example. So let's start off. What were the 3 things that we had to do when we were problem solving that we talked about last week? Right. We had to do a find,
Given,
and the last step, we're kind of tied in there, was our solution. So first, let's start with the find. What are we trying to find? Well, it's clear. How much does she owe after 5 years? And we said with a loan, the amount after a certain amount of time passes, what do we call that? Right, we had a couple of different options. Well, let's go back in our notes and look and see. Right, we had an amount. What is it called? Let's look here. Is it the principal? Is that the amount after 5 years? Is the present value the amount after 5 years, or is the future value the amount after 5 years?
future value.
Future value. So yes, we are trying to find the future value, right? The future value after 5 years. That's what we need to find. The future value after 5 years, right? So now let's move on to the given. What information did the problem give us? So if we look back at the problem is telling us Afia borrows $2,000. Is that important? Does that look important? Go ahead, Tanae. What were you gonna say?
The principal.
Okay, so we have our principal. Is how much? What was it? 2,000.
$2,000
And what else do we have? At
at a 5% annual simple interest.
yes, so that 5% is gonna be what? That's our interest rate. So our interest rate right? Our interest rate is 5%. That's our interest rate, 5%. And there was another little piece in there. What kind of interest is it? Go ahead, somebody's gonna say it.
Annual simple.
Simple.
Annual simple interest. So this is annual simple interest. And that classification is very important because that classification is what tells us how to approach the problem, right? That's what that classification tells us, right? And there's another given in here, right? That's kind of in our find, but it's also important to put it in our given, right? What's the other piece that we said is the most important part anytime we're dealing with finances?
Time.
Time. And how much time is passing?
5 years.
5 years.
5 years. So 5 years. The amount of time is 5 years. Now, going back to what we said about simple interest. Simple interest is when we pay interest only on our initial amount that we borrow, or only on our initial principal. Our initial principal is $2,000, and we are going to pay interest on that $2,000. We also said it's going to be the same amount each year. So let's start off. So $2,000 is what is owed in total, right? And then we need to add on the year one interest. And what's the year one interest going to be? It's 5%, right? So how do we find out what that's going to be? Well, we need to do 5% of 2,000. And how do we do 5% of 2,000? Well, first we need to change our interest rate into a decimal. As a decimal, that's going to be 0.05 times 2,000. And what's 0.05 times 2,000? 0.05 times 2,000, now would be the time to pull out your calculator. Do that in your calculator. But another way to think about it is 10% of 2,000 is 200. So therefore, 5% of 2,000 is going to be 100. Right? So our year one interest is going to be $100. So that's going to be plus $100. So after year one, what are we going to owe? Well, 2,000 plus the 100. After year one, we have to pay $2,100. Well, now let's move on to year two. And what do we say about simple interest? It's the same amount each year. So we're going to pay the same 5% of the 2,000. We already know what 5% of 2,000 is going to be. That's going to be another 100. And I'm sorry, at this point we don't owe $2,000. At this point we owe $2,100. So we're going to have to do $2,100 plus the 100, and we get our year two amount, which is $2,200. Everything is simple. And then year three comes around. We're going to do $2,200, which is what we owe now, plus the interest for the year, which is another $100. And that's going to equal $2,300. And then we go on for year four. We owe $2,300 plus the 100 that we owe for the interest for the year, $2,400. And in the last year, we have $2,400 plus the interest we owe for the year, which is going to leave us at $2,500. So in total, after 5 years, how much is Afia going to owe? She's going to owe $2,500. So that's how much we owe, $2,500 after the 5 years, right? And that was pretty simple. It's so simple because, well, it's simple because it's simple interest, but it's also simple because we're paying the same amount each year, right? That makes it simple because we have to pay the same amount each year. The amount doesn't change that we pay each year. So let's go back. This whole problem is worked out in here. If you go back and practice it, when you get to this point in the video where we introduce the problem, you should pause the video and try to solve through the problem. That's what you should do. Pause the video, try to solve through it, and try to see if you can solve it again yourself, and then you can watch how I solve it. Right? So future value after 5 years, so on and so forth. And here is a little table. It's the exact same thing that we did, calculating interest for each year, and we can see the interest is the same each year. And we end up with $2,500 that we owe. That's what we end up with. $2,500 that we owe. Now, the problem is that, let's say we were doing this for 20 years, right? If we were doing this for 20 years, would you really want to make a big old table like this out for the full 20 years? Would that even make sense? It wouldn't make sense. There has to be a quicker way to do it, right? If we were doing this, let's say she was borrowing this $2,000 for 20 years, it wouldn't be fun to like go out and say, okay, we add another 100 for this year, add another 100 for this year, so on and so forth, right? So what we need to do is find a better way. And the better way that we have is a formula. Now, our formula is basically a function that allows us to calculate the future value, F. F is going to stand for our future value. That is what we're trying to find. Let's put a little box around F because that's what we're trying to find. And that is our output. F is our output. Now, moving on, right? The inputs that we need to be able to find the future value, the inputs we need are the present value, which is P, or the principal. Right? We need to find R, the interest rate, right? That's another input we need. Now, another important note, when you get your interest rate, it's going to be as a percent, but we need to put our interest rate as a decimal. That's what we need to do. We need to put our interest rate as a decimal. We can't leave our interest rate as a percent. So in order to work with it, we need to work with it as a decimal. Very important note. And then we have T, which is the number of years or the loan term. All right, so let's go back to our problem and let's see if we can solve it using the formula. Right? So now what we're going to do, we're going to do a find given solution again, but this time we're going to approach it using the formula. So for the find, we had set up here that we need to find the future value after 5 years. But what letter did we use to represent the future value? F, right? So instead of putting future value after 5 years, we're going to say F after 5 years. That's what we're trying to find. And then for our given, what we can do, because you will get other formulas, right? So it's useful to first start off by listing what kind of formula you need. So for this one, since we only have one formula so far, we can list what kind of formula that we need. And for this problem, the formula that we need, this is the simple interest formula. And how do we know it's the simple interest formula that we need? Because look at what we put in our given. We put that this was annual simple interest. So we're going to start off there. We're going to classify the problem, and we're going to say annual simple interest. So we're going to start off and do. Classify the problem and say annual simple interest. Now, for our annual simple interest formula, we're going to start by writing it down. Our annual simple interest formula was F equals, and we're going to write this in our given, P times 1 plus RT. So let's write that down. P times 1 plus RT. And we know that we're trying to find F, but what do we need in our given? In our given, we need P, R, and T. That's what we need in our given. P, R, and T. Right? So we're going to list those out. So we're trying to find F. We need to know what P equals, what does R equal, and what does T equal. What does P equal in this example? Well, we already wrote it down, and it's almost like we wrote it in the same kind of way because we're writing P, R, and T. Here, we just wrote out the full words. Here, we wrote principal, interest rate, and time, right? That's what we wrote here. So P is our principal. What's that? $2,000. $2,000. What was R? What was our interest rate? 5%. So we're going to write 5%, but we need it as a decimal, so we're going to change it to a decimal, 0.05. And then for T, how much time is it? Well, it's F after 5 years, so we're going to write 5. Now for our solution, we don't even have to mess around with a table or anything like that. We can just plug these inputs. This is going to go in here. This is going to go in here. And that's going to go right in there. We can just plug those inputs in to our function, right? And once we plug those inputs into our function, we can simplify and it will give us F. So we're going to start off and do that. We're going to say F equals, and what are we going to put in for P? We're going to put in 2,000. Very good. Times 1 plus R. What's R? 0.05. And what's T?
Times 5.
Times 5. And now we just need to simplify it. And to simplify it, what do we use?
Right there.
So what do we start with? Parentheses, right? So we need to do parentheses first. So what's inside of the parentheses? 1 plus 0.05 times 5. So now inside of the parentheses, it's like we're going to do another little tiny PEMDAS. So we need to do this part first. And then after we do that part, then we can do the 1 plus part, this whole part, right? So let's do the 0.05 times 5 first. And we get F
25.
equals 2,000 times 1 plus, and what'd you get?
0.25.
0.25. Now we can add it together. So let's do another equals 2,000 times 1.25. I just added the 1 plus the 0.25. Right. Now we can do the multiplication. So we did the we did the P. Now we can do the multiplication. 2,000 times 1.25, and what do we get?
2,500.
So after the 5 years, F equals 2,500, right? So you see we got the same answer. And it's always useful to do it just so you can kind of trust that you're getting the same answer. That's why it's useful to do it like this, right? Do the same problem, do with the formula. So now everyone should trust the formula. Whenever you have an annual simple interest problem, right, jump right in here to this formula right here. That's what you should jump to. This formula right here for our annual simple interest. And whenever you hear annual simple interest, that's what you should be pulling out of your tool belt, right? So I want you all to think of all of the formulas that you all get. I want you to think of them all as being like a tool belt, so to speak, a tool belt of formulas. So for example, if I told you I need to put this nail into a wall, what tool do you pull out of a tool belt if you need to put a nail in a wall?
A hammer.
You pull out a hammer, right? So what you're going to do is a similar kind of thing. You're going to look at the scenario and say, what tool do I need for this scenario? Usually the problem statement will give you some clue as to what tool we need. So when you read the problem statement, look for the tool. In this case, right, what is the tool that the problem statement is telling us? The problem statement is telling us this tool right here. It's telling us that this is the tool that we need. That's the key part in the problem statement, telling us what tool we need, right? The key part. So look for that part, and then you can say, okay, I know what tool to pull out. So for whenever you see annual simple interest, the tool you should pull out is F equals P times 1 plus RT. That is the tool that you should pull out whenever you see annual simple interest. So moving on, right, here's another example. We're not going to do this example right now. I want you to try to work through this example on your own, right? So when you go and you study, try to work through this example. The answer is in here too, right? But I want you to try to work through this example on your own. But we're not going to work through it right now. So moving on, we're going to go to the next type of interest. The next type of interest is compound interest. Now with compound interest, it's a little different than simple interest. Because with simple interest, you just pay money, you pay on the money that you borrow, right? That's all you pay on, just the money that you borrow. But with compound interest, you pay on both the money that you borrow, or the principal, and all of the interest that you accrue since the beginning. So because of that, the amount you pay in interest increases every single year, right? Every single year, the amount increases because you're paying on both the initial amount and the interest that was added. And the interest is not based on the initial principal. Instead, the interest is based on the present value. Whatever the loan is worth then, that's how you calculate the interest. So before moving on, I want us to actually look at this same scenario where Fia is paying on a loan, and I want us to work this out, but with compound interest instead, with that little key difference. So with compound interest instead, right, we had the same scenario. We are trying to find the future value right? Exact same scenario. Future value after 5 years, right? And for our given, the first key difference is that this is compound interest, right? Compound interest, it's not simple interest. And our principal is the same. We're still borrowing the same amount of money, $2,000. Our interest rate is the same, still 5%. We're not changing that, right? Or 0.05, right? 0.05, 0.05, same thing. And the amount of time is the same, 5 years. So the only difference is this. That's the only difference. The only difference is that we're doing compound interest instead of simple interest. Right? So let's go ahead and see if we can solve this out using a table like we did the first time. So year one, right? What is Afia going to owe? Year one, $2,000, right? Plus, I'm gonna put Y1 interest. Now, how do we find the interest for Y1? For year one, we do the same thing. 2,000 times 0.05, right? 2,000 times 0.05. And what do we get? We get that this is 100. So everything looks good, almost the same. So at the end of year one, Afia owes $2,100. Now, who wants to be my loan shark? Tanae, you want to be my loan shark? So Tanae is the loan shark. And for year two, Afia comes to Tanae and it's like, all right, you know, I've done this before, so I know how this works. Year two, you know, I borrowed $2,000 from you, Tanae. Now, after year one, I owed you $2,100, and my interest is the same. It's the same $100. So Tanae is like, Afia's like, all right, Tanae, here you go, another $100 for year two. But Tanae says, no, sir, no, that's not how this works, because this is what? This is compound interest. This is not simple interest. You don't owe me
5% of that.
You don't owe me 5% of this. What do you owe? What does Afia owe you 5% of?
2,100.
She owes you 5% of 2,100. So we can't do a simple $100, which is 5% of 2,000. Instead, for year two interest, what are we gonna do instead? We're gonna do 2,000. Not 2,000, sorry, 2,100 times 0.05. And what do we get when we do 2,100 times 0.05? Now you owe $105 for this year, right? That's what you owe now. 2,100 times 0.05, $105. So after year two, Afia doesn't owe you, Tanae, she doesn't owe you $2,100, $2,200. After year two, Afia owes you $2,205. So let's compare year two here with year two from the other scenario. So in the other scenario, year two, what did she owe? $2,200. But you see now already we owe a little bit more. Already we owe $2,205. And for year three, it's a similar situation. Afia comes and says, okay, it's year three. I owe you $2,205, right? And I know what the interest fee is. The interest fee is $105, right? Isn't that the interest fee? Tanae says, nah, nope. It's not $105 because we got to recalculate your interest for the year. We're not going to recalculate your interest and base it on what you owed previously. This time for year three, right? We're not going to do the interest based on year one or based on what you paid in year two. This time we need a whole new interest amount. $2,205 times 0.05. Notice how the amount that you're calculating the interest on keeps going up. Like the first time we were just doing 2,000 times 0.05, but now the amount we calculate the interest on is continuously going up. And what's 2205 times 0.05? That's
10.25.
110.25. Yes. So now Afia owes you today. She owes you $23.15 and a quarter. And if you're doing all of this, believe you want your quarter. You're gonna be like, nah, I need that quarter. Go get some change. Go to the corner store, get some change. Because Tanae said, I want my quarter, and legs is gonna get broken if I don't get every single bit of my money. Because remember, Tanae, you a loan shark, so you gotta enforce it, right? So now, for year 4, what happens? Right now, Afia is getting hip, right? Afia is getting hip, and Afia is realizing what she has to do. She's realizing how she's gonna have to pay. So this is okay. I owe you $23.15.25, and then I'm gonna add my year 4 interest. And I know what my interest fee was last time. Last time my interest fee was $110.25. So here goes your extra $110.25. And what's Tanae say? What you tell her, Tanae?
Oh, you owe me $115.76.
Okay, so I don't know if your math is correct, but I think it is. It sounds correct. It's gonna be that $23.25 times 0.05. And what do we get? Times 0.05. Yep. 115.76. $115.76, and believe you want every single penny. So you said 75 cents. Nah, you want your extra penny because loan sharks.
Nah, I said 76.
You said 76? Okay.
True.
So now, after this year, she owes $24.31, right? And 1 cent. That's what she owes after now. $24.31 and 1 cent. And we can do the last year. So now she owes $24.31.01 plus our year 5 interest. Right? And now we should all be hit to the pattern. We're not going off the initial amount or the last amount. We got to calculate the interest again. And when we calculate that interest again, 24.31, 0.01, don't forget the penny, times 0.05, we get 121.55 plus 24.31.01. Okay. So after the 5 years, right? After the 5 years, we end up with a total of 2552.56. Right? And that is what Afia owes Tanae after the 5 years. And we can see clearly, comparing this amount, right? This amount here, right, to our previous amount when it was just simple interest, you can see Afia is going to pay an extra $52.56. Now, it may not seem like a lot, right? But think about what extra work did Tanae have to do to get that extra $52? No extra work. All she had to do was just change it and say, nope, it's not simple interest, it's compound interest. That is all Tanae had to do, right? And it added an extra $52.56. Right, that's all she had to do, and there we go, an extra $52.56. So you can see that even with everything being the same, compound interest is going to add up more, right? All things equal, compound interest adds up to more. And it adds up to more because with each step, we're not keeping the same amount. With each step, we're building on the previous amount. So here's like a little depiction of what compound interest versus simple interest would look like. Simple interest would be something like this, where you start off here, right? You go up as the same amount. Go over, go up. Each of these will be year 1, year 2, year 3, year 4, and year 5, right? So we end up here. This is where we end up. Dun, 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 we are in our house, right? So after each year, we go up by the same amount. Notice each of these steps are the exact same length. But with compound interest, on the other hand, we are not going up by the same amount. The amount that we go up by is based on how high we went up the last time, right? Or where we were the last time. So with compound interest, year 1 looks the same. So that's year 1. But then when we get over to year 2, instead of going to the next line, we go a little higher. And then year 3 passes, and then we go a little higher. Year 4 passes, and we go a little higher. Year 5 passes, and we go a little higher, right? So you can see how it's working. Well, this is where you end up here, and this is where you end up here. And that's because each step builds on the last step with compound interest. Each step adds a little more. Whereas with simple interest, each step is exactly the same. Each step that we take each year is exactly the same. Right? So going back, right, we can actually see that compound interest grows quickly because each step is again built on the last step. Right? Now, here's the thing. You can get even more greedy, right? So if Tanae was really greedy, Tanae didn't have to say, oh, I'm just going to compound at the end of the year. Instead, Tanae could have said, instead of compounding at the end of the year, I want to compound and collect interest from you every month. Or even I want to compound and collect interest from you every week. Or Tanae could be like, I want to compound and collect interest from you twice a week or every single day. Or Tanae could be like, I want to collect interest from you every second. So every second that you are awake or alive, the amount that you owe me is going to increase. And there's actually a way to do that mathematically, right? A type of interest. For right now, we're not going to deal with the every moment compounding. We're going to deal with what if Tanae said, I'm going to compound every year versus if she says I'm going to compound twice a year or 4 times a year or 12 times a year, right? And basically the way it works is that you're almost splitting up the amount of interest that's owed over the whole year over each of these little periods, right? So let's say you have to pay a total of 12%, right? If you have to pay a total of 12% a year, you could split that 12% up each month and then compound it. So you'd split it up each month and it'd be around 1% each month. And then when you compound it, you're not compounding the 12% over the whole year. You're doing that compound practice that we were doing, but you're doing it at the end of each month. So at the end of the month, you say 1% of what you owe me right now. And the next month, you say 1% of what you owe me now. And the next month, you say 1% of what you owe me now. So yeah, over the whole 12 months, you technically are still charging an interest rate over the 12 months of 12%. But what you're doing different is that you are splitting that interest rate up into each month. Splitting it up and then compounding on a faster period. So the way you know that compounding is happening on a faster, faster than just once a year, is you'll have these kind of what you call helper words, right? I'm gonna call them helper words, and those helper words help us to know how often we're compounding. So if you see compounded annually, that is compounding one time per year. If you see compounding semi-annually, that's 2 times per year. If you see compounding quarterly, that's 4 times a year. So you're compounding at the end of each quarter. And if you see compounding monthly, that would be 12 times a year. Or if you see compounding daily, that'd be 365 times a year. Now, it doesn't have to necessarily be these because, if you, whatever, I mean, let's say Ciara's like, okay, Tanae, you compound 4 times a year. I like the number 72. I'm going to compound 72 times a year. Ciara could do that, right? She could say compound it 72 times a year and it wouldn't change anything. All it would change would just be the number of times you compound it is 72 times instead of 4 times or 1 time. With the example we just looked at, we were looking at compounding 1 time a year. That's all we did, right? Look at it here. We compounded at the end of each year. So at the end of each year, that's when Tanae was, recalculating the amount of interest that was owed. At the end of every year, that's when you recalculate the amount of interest that's owed, right? But again, we don't have to do it on that period. So let's get a formula because again, just like we did last time, but this time it's even more difficult because you would have to literally calculate it out. And if you were doing it quarterly or daily, no one's going to sit and do it 365 times and then, do it 365, do this process 365 times for each year that it's going on. So what do we need? We need something to make it easier. And what are we going to use to make it easier? We're going to use a formula, something that can allow us to calculate how big each of these steps is going to be, right? Regardless of how many times it's compounded per year. Let me just give a little visual depiction really quickly of what it looks like to compound more than once a year. Let's say we compound it 4 times a year. Notice here how we go year 1. What we would do is we would split this into 4 equal parts, 4 quarters. And then we go up on the first quarter. We go up a little bit. Then we go up a little bit. We go up a little bit. Then we go up a little bit. And then we go up a little more. So it ends up being a little higher than if we compound it because we split it up into 4 pieces and we did the compounding more regularly, right? Interest rate is still the same, but the amount of times we compound it is different, right? So that's basically what it would look like. So going back over here, let's get a formula for compounding. We already did an example like this, but this is another example. The difference is a different interest rate and a different amount. But we already did this example. Basically, we used 2,005%, but in this example, it's 3,007%, and then the amount of time is a little different. So let's get our formula first. This is the formula for, and hold on 1 second. I'm gonna delete these. Let's delete these. There we go. So this is our formula, right, for compound interest. This is the formula that we use for compound interest, right? And in this formula, you can see that what we're usually trying to find is the future value. And then we need to know the present value or the principal, right? And then we need to know R. We need to know T, which is the number of years. So those things are exactly the same as the simple interest example. But the only new factor, the new input that we need now is how many times we're actually going to do this compounding in a year. That's the new thing that we need. How many times are we actually going to compound it? And that is this, N, the number of times we compound in 1 year. So in our example here that we did, what would N be? In this example, what would N be? Anybody? How many times were we compounding in this example each year? How many times were we compounding?
Once, because it's annual.
Yeah, in this example, we just compounded at the end of the year. See, we did year 1 interest, year 2 interest. We compounded at the end of the year. So in this example, we could add our N in there, and N would equal 1. Now again, Usually the problem will say it. The problem will say something like annual. It will say annual or compound interest compounded annually or something like that to tell you 1. So if you see compound interest annually, you know that n equals 1. Right? So that's the only new thing that's added in there, that n equals 1. Besides that, this is our formula. Now please note this is n times t, right? That is an exponent, and that we need to multiply n, whatever n is, times t. And what I would recommend is that when you write it out, you just do that part first, right? When you write it out, do n times t first. So in this example, n is 1, t is 5. If we were plugging this into the formula, we would just do 1 times 5 first. And when we do the 1 times 5, we will put that right in there, and that way we don't need to worry about the multiplication in the exponent. Right? We don't need to worry about it. So that's what we need to do first. So moving on, let's look at another formula. So we're going to get 2 formulas for this compound interest thing. The second formula that you use a little less regularly, the second formula is for when you want to know what you needed to start with, right? What you would have had to start with to know, to end up with a certain amount. So let's say instead of borrowing money, right? Let's say instead Afia was investing money, and Afia wanted to know how much money she would need to invest initially to end up with, say, $5,000. And she knew what principal, she knows what she wants to end up with, $5,000. She doesn't know the principal, so this is a question, but she knows what interest rate she can get because she looked at different banks and different investment opportunities. So she has a sample interest rate. She knows how many years she has to save up to $5,000. That she wants to save up $5,000 in the next 3 years, right? So she knows how many years she has. It'd be 3 years, and then she will look at how many times it's compounded. She would need to know that as well. How many times is it compounded? It might be compounded once a year. If you don't have something explicit, like let's say you get a quote from a website or something and it doesn't explicitly say compounded monthly or compounded annually, right? Which usually it'll be either one. Either it'll be compounded monthly or compounded annually, right? But if you don't see it, you can just assume that it's compounded annually. So you just assume n equals 1. But this is how we would find how much you would need to start with to end up with a certain amount. So now we have 2 different formulas that we can use. So let's do an example. We'll do an example with the first formula. So what we want to do here is let's compare a savings plan that pays 6% simple interest versus another plan that pays 6% annual interest compounded quarterly, right? And the question is, if we deposit $8,000 into each savings account, how much money will we have in the account after 3 years? That's the question. How much money will we have in the account after 3 years? So I want you all to work this out. What I'm actually going to do, I'm actually going to put you all in little breakout rooms. So one of you all will be by yourself, but I'll join in and I'll be your partner for whoever's by themselves. So again, this problem is solved in the slides, so you can always look through it and look at the answer from the slides. But find, we got 2 finds: future value for the simple interest account and future value for the compound interest account. For the given, P is 8,000, R is 0.06, T is 3, and for compounded quarterly, N is going to be 4. So here's our solution. For the simple interest, is relatively straightforward. We just plug everything in. The answer should be 9,440. Did y'all get that? Who got that? Who got 9,440? I think both of y'all got 9,440. Yep. Okay. Yeah. And then for the compound interest part, plug in all the numbers. Right? Notice what we did when we plugged them in. We just started off and plugged them in. And then what's the first thing that we want to do? First thing we're going to do this up here, which gives us 12. And because I was out of space, I did this at the same time, which gives us 0.015. Then we have this, 8,000 times 1.015 to the 12th. So you need to do this in your calculator. Right? That's what you need to do in your calculator. Now in your calculators, there'll be one of a few buttons that let you do an exponent. One of the buttons will look like this, X with a Y at the top. The button might look like an X with a little box on it. It might look just like this, like a little up-facing
That's the
arrow,
one I use.
right? It might look like, I'm trying to
I
think.
got a question. Do you have to put them in parentheses when you type it in the calculator? See
No,
how I put it? Okay.
no. So
Would that mess up your answer if you did do that?
no, it won't mess up your answer if you put it in parentheses. If you were putting the multiplication in the parentheses in the exponent, then you would need to put it in parentheses. But if you just put in one number in the exponent, you don't need to put it in the parentheses. So one of these three, I don't think you'll have anything different than these ones, because I think this is what almost all calculators have, one of these three. Even your phone calculator, I think your phone calculator has the X, comma, Y thing, but let me open up my calculator and see exactly what it is. Now, one thing you can do, if you all open up your phone calculators, right? And then you may be like, wait, it doesn't have anything extra. It's just like a 4-function calculator. But can you all see my picture here? Me?
Really?
Okay, well, this is all you need to see. Turn it sideways.
We also have an Android. We probably all got iPhones.
Open up the calculator and turn it sideways. Turn your phone sideways. Open up the calculator. Yep, just like that, Tanae. Yep, just like that, Ciara. Look at your phone.
Oh.
I love
Oh,
it.
yeah.
Open up the calculator and turn it sideways.
Oh, wow.
So everybody should do that just so you can see. And then after that, you do that. This is what you get: 9,564. So it looks like Tanae and who else was in your group? Tanae and who?
Janae Williams.
I'm sorry.
Hold on, who was in your?
Janae Madison, Pre-K Shining Stars.
Janae was in your group. I thought Janae was the person who said they didn't get it; they were stuck.
No, it was me and her, and then you had came on there.
Oh, so then what was the other? What the other group get?
We didn't do it.
Oh, y'all were stuck. Okay,
We did the first one. We ain't do the second.
gotcha. So y'all two.
And I left out the exponent part.
Okay, gotcha.
That's where I messed up.
Okay. So again, it's just PEMDAS, and you just have to take it step by step, right? Step by step. So Tanae and Janae are going to get our extra credit for today, and that was not intentional rhyming, but that's what gets our extra credit for today. All right. So moving on, we have another example here, and what we want to do this time is we want to consider if instead of compounding quarterly, what if we compound it monthly? So if we compound monthly, n is going to be 12 now because it's monthly instead of quarterly. Quarterly n was 4, monthly n is 12. So what I want to look at is this main thing, this right here. I want to look at what the difference is. You can see that when we compound it monthly with the same APR is the same. Notice the APR didn't change. APR is our annual percentage rate. That's another way of calling the interest rate, right? Is by calling it the APR. So our interest rate didn't change. The only thing that changed was how often we compounded and what happened. It was still compound interest. When we compound monthly instead of quarterly, we get like an extra, $9 over the course of the 3 years. Seems small, but imagine if you've given out 10 million loans. 10 million loans, that extra $9, that's an extra $90 million, right? If you give out 10 million loans every year, just by compounding monthly instead of quarterly, you get an extra $90 million, right? So, and also it would be much more than $10 if this was going on for more than 3 years. So again, time is the biggest factor that makes the difference, right? But the way this being solved, it's solved in the slide so you can look at it. But the main thing I wanted to show you is that even if we keep everything the same and we still have it as compound interest, if we compound more times, the more times that we compound, the higher the amount would be. So here we compound it more times, so the amount, the future value went up because we compounded more times. So moving on, there is another idea. The other idea, right? What if we wanted to compound every moment of every day of every second, right? We're not compounding 12 times a year. We're not compounding 365 times a year. We are compounding literally every moment. And that is called continuous compounding. And this is the formula for continuous compounding. So for continuous compounding, we have the future value equals the principal times E. And now please note, E is a number, right? And if you look on your calculators, you will see E in your calculators, and either it'll be like this, E to the X, or it'll be like this, E with a little thing over it, or it might say E to the Y, right? Either one of those. And you want to put that in your calculator to be able to raise it to a power. That's what you want to use to raise it to a power, right? Because we're raising E to the power, and the power is R times T. So we have F equals P times E to the R times T. So let's go back over here.
So E is always 2.71?
It's 2.71. So if you can't figure out how to put E in your calculator, you can just put 2.71 in your calculator for E. It won't be exact because E is like I'm sorry.
It's like pi.
It's like pi. Yes, it goes on. It doesn't terminate and it doesn't repeat. It just goes on and on and on and on forever. So if you just put 2.71 in your calculator, you'll be missing off a little bit. But it's not that big of a deal. So if you can't figure out how to put E in your calculator, just do 2.71 and your answer will be very, very close to the correct answer. So let's do the same example that we had just done previously, where you all had to split up into groups. But let's do it if it was continuously compounded. And then we'll be able to compare monthly, continuously, and quarterly and see which one is the greatest. So if I'll find... Same find, it was F after how many years?
3.
I think it's 3 years. And then for our given, this time we are doing continuous compounding. Compounding, and our formula is F equals P times E to the R times T, right? You can almost think of this as being in parentheses. The R times T isn't being in parentheses. That is without doubt what you want to do first, right? And for this, we can see the inputs we need. We need to know P. What was P? I think P was 8,000 in that example. What was R? R was 0.06 or 6%. And T was 3 years. T was 3 years. So now we have 8,000.06 and T equals 3. Those are the only things we need for continuous compounding. So now we can plug these numbers in and solve. We're going to go down here to our solution. And for our solution, we'll plug the numbers in. So we have F, which is trying to find the future value, equals 8,000 times E to the 0.06 times 3. So we're going to do that part first. And we'll get 8,000 times E. 0.06 times 3 is what? Is it 0.18? 0.18. Now we need to plug this into our calculators. E to the 0.18. E to that power. That's what we need to plug into our calculators. So what we'll do, I'll actually open up my calculator on here and I'll show you what button we're looking for. So to plug that into our calculator, the button we're looking for is, see the double E's down here? And see that E to the X? E with a little X on it? That's the button that we're looking for right here. Now on your calculators, that E to the X, it might be a secondary function, and the secondary function might be on a button that looks like this, LN. So look for an LN button on your calculators, and that E to the X might be right above it as a secondary function. So everybody find that on their calculators? And if you're using your iPhone or something, it might be an e to the x by itself. You might be able to just see it by itself, right? So we're doing e to the 0.018. And what you want to do in your calculator, depending on how it works, so let's see how mine works. Yep. So on mine, I press the shift, right? Press shift, and then I press the button e to the x. And then I type in the number, 0.18. And this is what I get out, 1.97. 1.197, I'm sorry. Now, on your phones or calculators or whatever, you may have to type in the number, the 0.18 first, and then type the e to the x button. But I want you all to play around with it until you get that 1.917 number, because that's what the goal is, to get that 1.917 number. Once you get it, remember what you did to get that number from doing e to the 0.18. So you just put a thumbs up when you get that number. Has anyone gotten it yet? Thumbs up, thumbs up. Janae, what about you? Thumbs up from Sierra. Janae? Janae?
Not yet. I keep forgetting my mute on. Not yet. I'm doing it now.
All right. And Darnitrice, what about you? Darnitrice?
Yes.
Sorry. What about you? Darnitrice, what about you?
Yes.
You got it?
Yes.
Okay, good. Janae,
Yes.
show me what you got on your thing. Show me what you got on your calculator. What kind of calculator are you using first?
I was using my You said what kind of calculator I was using?
You using your phone calculator?
The iPhone.
Okay, so put 0.18 first. 0.18.
Mhm.
And then put that E button.
Okay.
You did it?
I'm not getting this thing. I'm not.
What you getting? Show me what you got.
Can you see it? 2.7. You see it?
Let me see.
I don't think I
Where's
did
your
it
E
right.
button? Okay. Put.
Okay, let me clear it out.
Clear
Okay.
it. Type in.
She gotta do the EX because we got on the iPhone it say EX and then they have an E and then they have an EE. So
So I did the E.
So do
you
the
wanna
EX.
Do EX.
Okay.
So you don't want to
So
do
you
the
said-
E by itself. Do the EX. Put
So you
the
said 1.8.
0.18
1.8.
and then push that EX button.
Okay, I got it now.
Okay, awesome. So everybody got it. Everybody figured out how to do that. So now you know how to put that kind of exponent into your calculator. Now you know how to do that, right? So from here, we need to just multiply it by the 8,000, and we get 8,000 times, what did we get? 1.197, and we end up with 9,576. So that's how much money we end up with. 9,576. So $9,576. That was continuous compounding. And then let's look back over here and see what we had for the other ones. For monthly, we had 9,573. And then for quarterly, we had 9,440, I believe. No, 9,564.95. 9,564.95. And so we can see clearly that continuously is bigger than monthly, is bigger than quarterly. That's what we can see clearly, right? The more times we compound, the larger the future value will be. The more times you compound, the larger the future value, right? So that's what you should see and understand here. Now, you should be able to pull out the correct formula depending on the situation. That's what you should be able to pull out. You should be able to look at it and say, okay, this problem says compounded continuously. What tool do I pull out for compounded continuously? I pull out the F times P. F equals P times E to the RT formula. What formula do I pull out for compounded monthly or quarterly or any times per year, n times per year? I pull out the F equals P times 1 plus R over N raised to the NT power, right? And then for simple interest, what formula do we pull out? We pull out the F equals P times 1 plus RT.
Wait, is it 1 plus RN? No, what you
P
say?
times 1 plus RT.
Okay.
P times 1 plus RT. Right? So again, think of it like a tool belt. Right? What tools do you have and what is the situation calling for? So going back to here, we were here, we did an example. This is another compound interest example for continuous compounding. So you can follow along with this one, right? And if you get to this point, what you should do, if you're watching the video or you're looking through the slides, you should pause it here. Try to solve it yourself and then look at the answer. If you look at the answer first and then just try to look over it, it won't be effective. So pause it, try to solve it, and then look at the answer. That way you can see where you made a mistake or where you went wrong. So moving on, here's the solution. So we're gonna ignore this we're gonna ignore that slide for a second. And what we're gonna do, I do want to introduce a certain idea, but we're gonna ignore this slide. So we're gonna ignore the formula on this slide. Let me say that. So let me do this. What I'm actually gonna do, I'm gonna delete all of these. And what I'm gonna say is this. We're going to ignore this formula because we will get a different formula for calculating it. But I want to introduce the idea of what the APY is. And the APY is basically like the actual amount, the actual interest rate that you go up by. So notice, for each of these, what was the interest rate for each of these? Quarterly, continuously, monthly. What was the interest rate? This one was 8%, right? This one was 8%, right? And this one was 8%. And if we did it any other kind of way, like let's say we did this annually, we would get another value. And if we did it, every day, we would get a different value. So the question is, if you are quoted an interest rate of 8%, how do you know which value you end up with if all you're told is that the interest rate is 8% and you know it's compound interest? That's where the APY comes in. Because the APY is the actual interest rate. And basically what the APY does is it looks at how much is your amount going up by on an annual basis. And you can see that obviously this one goes up by more every year than this one does, which goes up by more every year than this one does. Obviously, the interest rate, the actual interest rate here is going to be more than the actual interest rate here. They both can't be the same 8%. I mean, yeah, that might be what you quoted, but clearly they both didn't end up in the same amount, right? Since they clearly didn't end up in the same amount, we need some way to accurately compare the two. And in order for us to accurately compare the two, we use the APY, right? Now, I'm not sure if I mentioned it before, but the interest rate, we can also call the interest rate the APR, or the annual percentage rate. All right, so that's another name that we can call the interest rate. So for all of these up here, the APR, or the annual percentage rate, or R, is equal to 8%. But the APY is different for each of them. So the APR for each of these is 8%. But because they're obviously not giving us the same amount, we know the APY, or the actual interest rate, will be different. And basically the APY can be one of two things. If the APY, if it is compounded annually, so in a situation where it's compounded annually, then we don't have to worry about anything. The APY is going to equal whatever interest rate we were quoted, or the APR. But if it's not annual, any other period of time, compounded continuously, compounded monthly, any other period of time, then the APY will be greater than the APR. And again, the APY is the actual interest rate. There are actually laws now that say that whenever you borrow money, right, companies need to give you the APY. They need to. They have to, by law, right? Then they have to include all of the fees that you pay on that money. They have to include it and give you what interest rate are you actually paying for whatever you're borrowing. So if you buy a house and you take a mortgage out, your mortgage company will tell you this is the APY, right? If you buy a car, your car company will tell you this is the APY. This is the APR. This is the APY. No matter what money you take out, your credit card statements, look at your credit card statement agreement. If you look at your credit card statement agreement, you will see the APY in addition to the APR, right? So that's what the APY is. It's like basically the actual interest rate, whereas the APR is the quoted interest rate. This little note here is important, right? This little note here is important. This here is what tells us what the APY and the APR will equal. Either it's going to be bigger than the APR, or it's going to be the same as the APR. It won't ever be less than the APR. APY is always going to be the same or more than the APR. Right? And the reason why I said we're going to just ignore the formula here, this formula for finding the APY is a little clunky. And next class, we'll actually get a different formula for finding the APY that's a lot simpler and more straightforward. So really quickly, what I want us to do, I want to look at just a general overview of what we talked about today. Now, today, going back up to the beginning, we talked about simple interest. We talked about compound interest. And next class, we're going to talk about these ones: investments, savings plans, and loan repayment, right? So now, in building your tool belt, right, when you read a problem and you approach a problem, here is the thought process that you should go through. So you approach a problem and you see, okay, this is a money problem, and there is some kind of interest involved. So the first question you want to ask: simple or compound? And we'll do this like a little flow chart. So we're going to start off, and I'll draw you. Well, let's do it like a flow chart. So the first we get here, simple or compound. If it is simple interest, good news, you're basically done. We just go to the formula. F equals P times 1 plus RT. And that's all there is to it. If it is compound interest, then we need to say, is it compounded? We'll say N times a year, or is it compounded continuously? Right? And N times a year just means, it's 1 time a year, 5 times a year, whatever number N is, quarterly, monthly, whatever. And then if it's N times a year, then congratulations, you're basically done. We get this formula: F equals 1 P times 1 plus R over N to the N times T. And I'm going to put that in parentheses. And if it's compounded continuously, then we get this: F equals P times E to the R times T. And I'll also put that in parentheses. So now you have 3 different tools in your tool belt. And now you have an idea of how you can figure out which tool to access. Think about it like what we said with a hammer. Right? You see a nail needs to go in the wall. You need to say, what tool do I need to pull out? If you see a screw, are you going to pull a hammer out for a screw? No, that don't make no sense. You're going to pull a screwdriver out for a screw, right? That's what you pull out for a screw. You pull a hammer out for a nail, screwdriver out for a screw. If you need to cut something, maybe you pull out some scissors or a saw or whatever. So it's the same thing here. Start off at the top and then say simple or compound. And if it's simple interest, you just march right over here. But if it is compound interest, you need to ask yourself an intermediary question and say, is it n times a year? Which would be, again, is it annual, monthly, quarterly? It could be daily, bi-weekly, semi-annually. You got to look at the word and see what the number is. And then if it's not n times a year, then it's continuously. And if it's continuously, you're going to go down to this one right here. So this is kind of like a little flow chart that can help you, right? And help you think about it. I want you all to think about each of these formulas that you get as a toolbox. It's a toolbox, and you are building your toolbox. That's what you're doing. You're building your toolbox. Okay? All right. So does anyone have any questions for me before I turn off the recording?